Hello and welcome to another video in this series as we journey from the simple primes to the foothills of the Riemann hypothesis. Today we're going to be doing something a little bit different, a bit unusual, in that we'll be exploring an experimental approach to mathematics. So when we find that we're struggling with a particularly difficult problem in mathematics, and our normal approach of using logic and analysis and proofs isn't helping, it can be useful to explore the problem experimentally. Now, we've already said a few times that experimental evidence isn't proof. We in mathematics only rely on strong, firm, indisputable logic. We want to see eventually assertions proved in a way that can't be argued with. So examples and experimental evidence isn't proof. However, looking at experimental evidence can give us hints and suggestions and pointers as to where to direct our work. So it's a useful thing to do when we're kind of struggling with something or finding something to hold on to and explore further. So let's see how experimental mathematics can help with this really knotty problem of the prime numbers. And we're following this not just because it's interesting in itself, but also it's because it's how historically some of the most important advances in the mathematics of prime numbers were made by inspiration from experimental evidence. So what we're going to do is think about the number of primes up to a given number. We're going to ask ourselves the question, how many primes are there below a certain number or up to a certain number? Now, some of you will have brains that work in a different way and want to ask, what's the average number of primes in a given range or up to a number? But the two are equivalent because one is simply the other one divided by n, so the number of primes up to n divided by n is the average number. So essentially we're asking this question, what's the average number of primes? Now we can't say what's the average number of primes over the entire number line because that's infinite. What we can start with is to say, well, what's the average number of primes in a given range? And the simplest range is simply from 0 up to n. This symbol you're seeing on the screen, this pi n, it looks unusual. It looks like it's a function, and it is. It's not pi in the sense that we're used to. The number 3.14. It's not the ratio between a circle's perimeter and its radius. It's just shorthand for the number of primes up to and including n. It's a bit unfortunate because it can be confusing, but once you understand the context of what you're reading, you'll be able to see straight away when the meaning is this and not the other number. So let's look at a few examples. So here's just a listing of some numbers from 1 to 13, and the next row contains the number of primes up to and including n, which is this pi n function. And you can see for 1 there are no primes up to and including 1. 2 is a prime, it's the only one that's an even number. So the number of primes up to and including 2 is 1. 3 is also a prime, so we've increased our count. The number of primes up to and including 3 is 2, those 2 being 2 and 3. Now 4 is not a prime, so that count doesn't change. That's sort of a cumulative count. And you can see every time we encounter a prime, that count goes up. So 5 is a prime, so 2 becomes 3. 6 isn't, so 3 stays 3. So just for clarity, the number of primes up to and including 5 is the same as the number of primes up to and including 6, because 6 is not a prime, and so on. And the first thing we notice when we look at this row of numbers is, well, it's growing. There's some repetition there, and if you decided to kind of carry on this calculation for more numbers, it might not be entirely obvious whether there's a pattern there. I mean, it's not even easy to say how often these things will repeat, which is another way of saying when is the next prime. That's, as we know already, that's not easy to predict, in the sense there isn't an obvious simple formula that captures that. But since we're taking an experimental approach, why don't we plot a chart comparing n with pi n and see what happens. Wow, okay. So this is showing the number of primes up to and including n, where n goes from 0 to 100. So it's quite a larger range, and we can see that there appears to be a smoothness to this chart, which is a little bit unexpected. We started with this intuition, this feeling that the primes were kind of random in some sense in how they're located on the number line. They were hard to kind of predict. Sometimes they clump together, they're just two apart, and sometimes there's long gaps. So what this sort of suggests is actually there's some constraint at play governing the primes, so that this curve that's emerging is as smooth as it is. There's a reason that we don't quite see yet as to why this curve isn't more chaotic or jumping around more than it is. And that's a really important thing to kind of understand. Something is governing the location of the primes such that this curve is as smooth as it is. That's really quite enticing. And Gauss and others were very, very intrigued by this, and it was something they latched onto as a basis on which to then do more traditional mathematics. In fact, Gauss used to, just for fun as a teenager, just count the number of primes in intervals, like up to 1,000, then up 1,000 to 2,000, then 2,000 to 3,000. Not many children would be doing that for fun, but he did, and he was able to kind of see this kind of pattern emerging. An interesting question to ask is, well, what simple mathematical function matches this curve? Initially, I'd say it looks logarithmic, but it might not be. But it kind of has that sort of shape. So that's something to kind of hold on to, this idea that there's something logarithmic about this curve. So Gauss was the first to approximate that function, this prime counting function, fairly well. I mean, he was 15 years old, and that's pretty amazing. And the formula he came up with was surprisingly, shockingly simple. Simply n over log n. And if we plot that, we'll see that actually it seems to match that experimental data fairly well. Now, the thing to ponder on is, one, wow, that really is simple. And if it's so simple, does that mean there's some simple pattern or law governing the primes that we've just not been able to kind of grasp onto yet? It certainly is tantalizing. It's certainly kind of suggesting that. It's certainly teasing that there is. I think that's quite shocking, that something as impenetrable and difficult to kind of analyze as the primes seems to conform to something as simple as this. Just to repeat, this isn't an exact match. This simply is saying that the experimental data, when we look at the number of primes up to n, seems to match this fairly well. He also, just a year later, developed an even better approximation, and it's this thing here. Now that might look a little bit scary initially, but it's simply an integral of 1 over the logarithm of x, integrated from 0 to n. Some textbooks will say 1 to n. It doesn't really matter too much, because as n gets larger, the difference is negligible. And as we'll see later, there's another reason why we can not worry too much about that difference of starting from 1 or 0. We'll see that in the next video, actually. But this approximation seemed to be matching the data even better, and that's kind of enticing. Again, it's still very simple, and again, at the core of it, there's a logarithm. What does that mean? What does that tell us? What is it teasing us with? Just in terms of terminology, this thing is called a logarithmic integral, and it's often written as Li brackets n or Li brackets x, a logarithmic integral. Now, if you step back and look at it, you might say, well, this is simply a continuous form of the other more discrete approximation. Let's look at that one again. There it is, n over log n. Let's draw a picture to kind of explain what we mean there. So what do we mean by a continuous form of a more discrete expression? So if we say we've got, 1 over n summing up like this. So these are width 1. So the height of these is 1 over n. And if we add them all up, we're adding up all these little bars. So we're in some sense counting the area of these bars. Now you'll remember from school that one way calculus and integration was introduced was to work out the area as this width got smaller and smaller. So we had ever thinner bars to count the area under the curve 1 over x more accurately, and that was 1 over x between the limits like b and a dx. So this was a continuous form, in some sense, of this more discrete expression. So in some sense we're saying that if we're becoming more and more accurate about some function as we work out the area, we arrive at this continuous integral. So that parallel is interesting to see. So let's look at comparing the two approximations. On this chart now we're going from n is 0, not to 100, but 10,000. And you can see the curve still looks fairly logarithmic. The dotted line is the true number of primes up to and including n, and you can see the simple approximation n over log n does follow it fairly well, but the other one, the logarithmic integral, the continuous form, seems to follow it even better. But the charts, if you look closely at them, so if we look at the simple approximation n over log n, the error, the difference, is getting larger. And although the other one is closer, if we did look at the numbers, we'd also find that the difference, the error, is getting larger. So does that mean that the approximations become useless as n gets larger because the error is getting larger and larger? And if we do, use a computer to do the calculations for even bigger n, we will find that the error just gets bigger and bigger and bigger. for both of those approximations. So should we give up? Actually, we can look at error in a different way. And instead of the absolute difference, the absolute error, we can look at the proportional error. Let me draw a picture of what I mean by that. So if I have some quantity that's supposed to be 10, but my approximation gives 9, the absolute error is 1, and my proportional error is the absolute error, the difference between the absolute error over what it should be, and that's 0.1 or 10%, and we can see that the error is 10% there. Now if we look at the proportional error, just call it PE for here for example, what we find, well actually let's look at a picture to see what we find. What we find is for both approximations, the simple one and the logarithmic integral, the proportional error is falling. Now that's really interesting. That's quite powerful as well, but it's really really intriguing that as n gets larger, the proportional error in those very simple approximations appears to be getting smaller and smaller and smaller. So perhaps those approximations aren't useless after all. We just have to think of and look at the error in a different way. Also worth noting here, and not a surprise, that the logarithmic integral, which was more accurate, does have a smaller proportional error, and we can see that straight off the graph. Let's kind of draw a picture again just to illustrate what we mean by the proportional error falling. So previously we looked at a quantity which should be 10, and we had 9 as an approximation. Now let's just say we've increased n, for example, or the number of samples or some other variable, and now we've got more, and let's say the answer should be 100, but our approximation is giving us 95 instead of 90. So here the error is 5, but the proportional error is 5 over 100 is 0.05, and that's smaller than 0.1. So as our sample size or some other variable has grown, our proportional error has fallen from 0.1 to 0.05. So although the actual error has increased from 1 to 5, the proportional error has shrunk from 0.1 to 0.05. Now, in other contexts, different measures will be useful, so sometimes the actual absolute error is important, and sometimes the proportional error is more important. But in this mathematical sense, it's just interesting to see that with the primes and these approximations, although the absolute error seems to grow endlessly to infinity, the proportional error seems to be growing smaller, shrinking towards 0. That's interesting, and it prompts a kind of it prompted a really important theorem which we will look at next time, but this is laying the groundwork for that. These are the observations that were made that laid the groundwork for one of the most important theorems in mathematics, called the prime number theorem, and it is to do with this kind of ratio we've talked about between the prime counts, the actual prime counts, and various approximations. But we won't dig in that today. We'll save that juicy morsel for next time. So this is interesting, and again, as a bit of experimental mathematics, this is fascinating. There's enough here to sort of say, well, this is definitely worth exploring more rigorously and mathematically, analytically. That's certainly a lot of strong pointers here. So just to illustrate that with a specific example. So if we have the first 10,000 normal numbers, and we count the primes up to and including 10,000, we'll find that there are 1,229 primes there. That's the actual number. The logarithmic integral, the better approximation, says it should be 1246. There's some decimal points there, but that's roughly what it will say. So the error is about 17. That's not bad. As a proportion of 1,229, that's 0.0138. And actually, if you want to try it yourself or look it up yourself, if you have even bigger numbers, you know, 1 million or 1 billion or even larger ones, this proportional error will get even smaller. So a question to ask ourselves, and we're not going to answer it today, but something worth thinking about, and we will explore it next time. A question to ask is, if the proportional error falls towards 0, perhaps these approximations are correct in the limit where n goes to infinity. That question itself is kind of making us think about some really interesting concepts, like, well, what does that mean? You know, if the approximations are actually wrong, but they're correct when n is infinity. And which one of those two? You know, one is clearly better than the other one. Are they both correct at n is infinity? And what about that pesky fact that the error was growing and growing and growing towards infinity? So what does it mean to say that they're correct at n is infinity if the error is growing to infinity, but the proportional error is growing to 0? Those are some really interesting questions to grapple with, and we will answer them next time. Now, just to step back again and draw some parallels, because you might sort of say, well, those approximations that Gauss came up with, you know, did they come out of thin air? And if they did, what do they mean? What does that logarithm in there mean? They looked simplistic. They looked really simple. There must be, you know, some interpretation of them. What do they capture? One kind of perspective on this is interesting. So if we compare a general expression for, you know, mass is density times volume, or number of things is density times length or duration or area or volume, you know, an expression that combines density times some volume or area or distance to create a total of some quantity. We can compare those general expressions with this approximation. So we can say the number of primes, is it some density times an interval or a size? Does this suggest that 1 over log n is the density of primes, an average density? Seems to suggest that, doesn't it? Over a duration or an interval on the number line n, if the average number of primes is 1 over log n, that gives us this prime counting function, or the approximation. That's interesting, isn't it? This suggestion that 1 over log n is an average density of primes. If this is true, that's actually quite it's quite an insight. It's quite a revelation. We hadn't really thought about it that way before, that the average number of primes up to n is 1 over log n. What does the other more accurate approximation tell us? Does it suggest the same thing? Let's have a look. And again, when we look at a more, you know, if we don't assume the density is constant, we then have to, you know, if it's continuously changing in a area or a volume or a interval, then we have to use continuous integration. And the expression is something like quantity or total or mass is the integral of a density, a local density, integrating it over the volume or area or whatever it is. Again, we can draw the same parallel here. The number of primes up to n in an interval when we integrate in a continuous way over a density which is 1 over log n or log x. So again, 1 over log x emerges as a kind of a prime density. And this one, this makes sense because this one was more accurate. And we know the prime density isn't constant. You know, the number of primes in the first 100 numbers is not the same as between, you know, 1,000,000 and 1,000,000 plus 100. So this is really intriguing. This is really suggesting in a very strong way that we explore more mathematically this idea that perhaps 1 over log x is some kind of locally accurate density of primes. You know, we'd have to define that, what that means more rigorously, but as an intuition, it's really enticing. Wow, yeah, exciting. We won't kind of explore that any further today. As we say, the next video, this is laying the groundwork for the next video, this kind of journey through some of the experimental mathematics that was done in the past, that laid the groundwork and, you know, set the pointers for some really important theorems in mathematics. But the history, you know, some of us are interested in, you know, the history of mathematics. It's a little bit murky because it's not entirely certain who did what first. You know, people didn't routinely publish their work, didn't leave a kind of a digital footprint. So we have to rely on piecing the history together by looking at, you know, what evidence we can find in letters and notes and so on. Gauss often didn't publish his work. You know, he wasn't very good at that at all. He was particularly bad at it. Now, somebody else called Legendre in 1797 published this expression that looks very similar to Gauss's, and it says it has the logarithm function in there, and it has, you know, 1 over log, but it's got some other constants. And that was in 1797, so that was quite early, so perhaps he was the first. And there would be a good case for arguing that. In his, you know, this was published in a book which is considered the first book on number theory. He published a second edition in 1808, and then he refined it, so the A became 1, but this B was this other constant. I think again later this was proven to be wrong, in the sense that if it was 0, that would be more accurate. But still, this is very, very early work. So perhaps it was Legendre who first came up with this really good approximation. In 1849, Gauss wrote to his friend Encke, who was an astronomer and I think one of his students, and he wrote saying that, quotes, in 1792 or 1793, so he's saying that he had done this earlier, that he had developed this expression, the integral one, the better one. He wrote it in a different form to what we would write today, so he wrote log, L-O-G, meaning natural log. But it's interesting that he asserts or claims that he did it first, and that he did it in these years before Legendre. Interesting. Do we believe him? He certainly was working with prime counts, you know, even at the age of 15. So there's nothing to say that he wasn't doing very important work at a very early age. If we look at the collected works, which you can find online, we saw that Gauss had written about in 1791, before Legendre, the simpler approximation, and he wrote it as A over LA, which we interpret to mean n over log n or a over log n. You can look at these primary sources yourself, or the letters and collected works. The blog that accompanies this video will have links, so you can have a look yourself. So do take a look there. But let's reproduce some here because it's interesting looking at historic works. So this is Gauss's 1791. I made a mistake there. I'll correct that for the slides. And you can see here the A over LA, and he wrote Primzahlen unter A, primes under A, A over LA, A over log A. So there we have it. It's fascinating to be able to actually see his own words, his own choice for how he expresses that expression. As I say, we'll provide the links so you can explore online yourself these early works. Legendre, when I said that he wrote it in 1797, it wasn't even the main narrative of his book. He wrote it as part of some footnotes. So here's the main text, and then in the footnotes he sort of says in French, it is true, or probably true, that some rigorous form that gives the value, I think, of the form b equals a over a log a plus b, where a and b are constant coefficients, and the log is the logarithm hyperbolic logarithm, which in those days meant the natural logarithm, log base e. It's really fascinating to go through these kind of primary sources. And this is the very famous letter from Gauss, 1849, and this is his own hand. This is his own handwriting, and there, right in the middle of the page, integral dn over log n is his way of writing the logarithmic integral. Fascinating. So I hope that's been a useful video. As we said, experimental evidence isn't rigorous proof, but it can strongly suggest where we might do rigorous work. And just walking in the footsteps of these mathematicians is really interesting to kind of feel and see what it was that inspired them towards the more important and now famous theorems of mathematics. So next time we'll dig into that a little bit deeper and look at the prime number theorem, which is important, quite famous, but simple enough for us to understand. And today's exploration of the difference between the absolute error, which was rising, and the proportional error, which is falling, that concept is going to be important. I can't wait. See you next time. Bye.